Swayam Prabha. Digital India. Educated India.
Until now, the problems what we have looked at for the deflections of beams, they were mostly statically determinate structures. And since they were statically determinate, it was easy for you to find the reactions and express the moment in terms of that reaction, and then plug into that equation ei d square y by dx square equals to moment of x. And then the only things you needed to compute were the constants of integration. Now, in this lecture, what we are going to look at is how do we deal with statically indeterminate problems where you do not know the reactions. We do not know all the reactions that are there in statically indeterminate problems simply from the equations of equilibrium. So we will see that how this is also one of the first places in your curriculum of structural engineering or civil engineering. You will see that how we can use some of the concepts of the deflection of beams to find the unknown reactions in statically indeterminate structures, and from that how can we find the deflection of statically indeterminate beams. So if we go ahead and take a look, so for example, you have statically indeterminate beams, maybe something like this over here, right? So here we have a fixed end at one end, it's a cantilever, so it's a propped cantilever. You have a cantilever and a simply supported end at the other. Now from here you can tell that this beam is statically indeterminate to degree 1. Why? Because you have a reaction here, a fixed end moment here, and you have a reaction here. So you have three unknowns, but your only saving grace are two equations of equilibrium. The one along the x direction doesn't matter, so you're only left with f of y equals to 0 and the the moment about a point equals to 0. So you have three unknowns, so you will not be able to solve for all the reactions using just the equations of equilibrium that is there, right? So these are the reaction components that is there. So you have this vertical reaction, this is vertical reaction, and this is the moment. Also you have it says that four unknown reactions. You have the horizontal reaction, but that is 0 in this case because you have no other forces in the x direction. So eventually you have three unknown reactions that you have, but two equations of equilibrium, right? But if you take a look at this beam and then if you apply, say, the general equation, see this equation what we have, it comes from the general equation itself for the moment. For example, the precursor to this equation is nothing but what we had seen earlier, that my ei d square y by dx square equals to m of x. If we take this one and if we integrate it 2 times, this is what we had seen before, you end up with two constants of integration. So you might be thinking that you're actually making your life worse because you already have one unknown reaction. Now on top of that you are introducing two constants of integration, but actually it is not. You're actually making your life easier because these three additional equations, these three provides the additional equations for the boundary conditions. And how does it do that? See, at this particular point we know that the deflection is 0, right? So that is one condition it gives you, that is y equals to 0 at x equals to 0, y equals to 0 at x equals to L. In addition to that, there is one more condition. Can you think about it? Yes. So here you see at this cantilever end, since it's cantilever over here the slope also must be 0. So ei dy dx must also be equals to 0. So although you are introducing your two more unknowns, you are providing three additional equations to take a look at that. And this picture essentially shows you that at x equals to 0, theta, that is the dy dx. So theta is nothing but your dy dx over here, that is 0, y equals to 0 and x equals to L, y equals to 0. So let's go ahead and take a look at a problem for the statically indeterminate beams. And also you must keep one thing in mind, that this method also that you are learning, that this only works when you have a continuous kind of, if your moment is a one single function along the length of the beam you are looking at. If you have discontinuities, the load and all, you will land up in problems with then, because in that case you have to have the continuity conditions of the deflections and so on. So first let's take a look at a simple example problem of a propped cantilever beam with a triangular loading. The example problem that you see, you have a propped cantilever beam with a triangular loading over here. What it asks you is to find the reaction at A, derive the equation of the elastic curve and find the slopes. It also asks you the slope at A over here. Okay, now if you take a look at this beam, you will have, since all the loads are in the vertical y direction, you will essentially have three reactions over here. You will have a vertical reaction Ra, here you will have a vertical reaction Rb, and since it's a cantilever end, you will have a moment Mb. There are three unknowns. Your equations of equilibrium, two equations of equilibrium are not going to help you. So here we will see that how our concepts of beam deflection helps us to solve this particular problem. Now for this beam also, if I draw a section at say any distance x over here, and if I write the expression for the moment at that one, so let's just go ahead and draw the free body diagram of this small chunk which we can separate out, and draw the free body diagram and find the moment, because eventually remember we have to go back and substitute to ei t square y by dx square equals to m of x. So if first I will draw the free body diagram of this one and write the expression for the moment. Now this triangular load can be replaced by an equivalent load which is acting at a distance of 2x by 3 from here, or x by 3 from here. Now once we have marked this, if you write out the equilibrium equation, you will get an expression for the moment as, this is the expression for the moment that we got over here, and now we are going to use this expression for the moment and substitute in our equation to get the deflection. So this is the expression we get. The first one is for the slope, and this is after you integrate it one more time over here. So now you see this equation has three unknowns. Your Ra is an unknown over here, and your C1 is an unknown, and your C2 is an unknown over here. But now with this one, you have now introduced three boundary conditions. Why? Because at this left end over here, at x equals to 0, my deflection equals to 0. At x equals to L, my deflection equals to 0, as well as at x equals to L, my slope, that is dy dx equals to 0. So let's go ahead and write the boundary conditions. So you have introduced three boundary conditions over here. You have three unknowns in this one over here. So you can, mix and match and play around with it and find out the values of the Ra, C1 and C2. So I will go ahead and write the values that we get over here. Remember, you have to use both these equations over here because you have an expression for the slope. So you can go ahead and try that out. I'm going to write the final expressions for Ra and C1 and C2. So this is, you see, using now our deflection criteria that we have over here. Now without using any equation of equilibrium alone, I have found out what is the value of Ra simply using the deflection steps. Now if you want to find the other reactions, the problem does not ask you that. It is now very easy to do. You can use your regular equations of equilibrium, that is a vertical load equals to 0 and moment about any of the points if you take as 0. Since Ra is already known, you can easily find Mb and Rb. We are not going to do that here since the problem does not ask that. However, the problem asks you to write the equation of the elastic curve. So from this equation of the elastic curve, I already know Ra, I know C1 and C2 over here, and it also asks us to find the slope at A. So this one over here, after substituting Ra and C1, we will get the slope at A by putting x equals to 0. So let me go ahead and do that. You can come back and check. So this is the slope and this is the equation of the elastic curve. So how do we represent the slope over here? See, you have over here, sorry, this is a negative slope. I missed the negative sign. So it is a negative slope that you get over here. So that means your beam, and as you can see from the figure also, the beam sort of deflects like this. So let's just draw the deflected shape of the beam. So here at this point, you see the slope must be equals to 0 over here because there's a cantilever end, and at this particular point your slope is this one, minus W naught L cube by 120 EI. So I hope this problem example was clear to you, that how we used our concepts for deflection of beams to find the unknown reaction and as well as the deflection or the slope at different points of interest in the beam. Now again, just to remind you, this was possible to do in our case and possible and easy to do because you had one continuous equation for the moment that is valid across the length of the beam. Now if you have intermediate disturbances like a point load or a point moment and so on, so did you really think that every time a structural engineer gets to solve a beam deflection problem, he or she goes and grabs a notebook and draws the beams and draws a free body diagram, writes the expression for the moment, takes care of the continuity conditions, evaluates the constants of integration after integrating it twice or 4 times if you're using the fourth order method, right? And then after all of this finds the expression for the deflection and the values of deflection and the slopes at different points? Well, no. In this lecture, we are going to learn about the method of superposition, in which someone has already done a part of the job for you. All you need to do is to use the principle of superposition and adopt certain things which are already established, and that will help you solve your beam deflection problem. So let's go ahead and take a look at that. Now, using the principle of superposition, before we get into that, let's take a look at this beam over here. So if you take a look at this beam, this is the 7th example problem in the list of problems which we have been doing. Now, so in this beam, if you see, you have a beam with a uniformly distributed load, and it's simply supported, and you have a 150 kilonewton load acting over here. Now, what the problem asks you is that the slope and deflection at the point D over here. Now you see this problem gets complex. Why? Because here now, in addition to the UDL, you have a discontinuity load over here. So to find the deflection at the point D, also the slope at the point D, not only do you have to have, remember this is the problem you solve in region 1 and region 2, you have boundary condition here and here. Now in addition to that, you also have to use what? You also have to use this continuity conditions over here. So you see it becomes increasingly complex over here, right? So what is an easy way to solve these kinds of problems? So if you take a look at this beam over here, and as long as you are within the linear range, you are having small deflections, you can split this beam into these two beams. So the first beam just has this load over here, and the second beam has this one over here, right? So we are essentially using the principle of superposition, where the total deflection for the combined loading can be obtained as a linear combination of the deformations of the individual loading. So here, by that, what I mean is, at the point D, if I compute the deflection for my beam 1 over here, so let me go ahead and mark these two beams over here. Let me say that this is beam 1 and this is my beam 2, right? So what you're trying to find, let's say one of the things that you have to find is a deflection at D. So your total deflection at D will be equals to the deflection at D for beam 1 plus the deflection at D plus beam 2. This is essentially your principle of superposition. That's what you are applying over here, right? So you are finding the total deformation or the total slope as a consequence of these two things over here. Now imagine if you have more number of loads, how many different beams you have to keep on splitting over here. And now you can go ahead and, using the second order method, you can evaluate the delta D B1 over here, second order method for this one over here. But now if you have more number of loads, if you have to go on, keep on doing the second order method over here. But now, so this process, and you will love it, this process is facilitated by the use of certain tables which are found in textbooks. So if you look at any of the recommended textbooks for our course, you will see that this is what it says over here, that this process is often facilitated by deflection tables. So if you see at any standard textbook, take a pick any of the recommended textbooks which is in this course, and if you go to the back side where you have the appendix and some of the standard tables and so on, you will often see a table like this. So what this essentially gives you, let's maybe pick one of them and see. For example, let's maybe go back to the previous one and see which one we can pick. Let's say this one over here. So what we have is a simply supported beam with a point load at a certain distance, not at the center, at a certain distance. Now let's go back and look at the table. So if you see this table, let's pick that out. Okay, so you have one case over here. where you have a simply supported beam with a load P at a certain distance, not at half. At half also you have a separate one. This is a more general case. Over here at a certain distance, it gives you the elastic curve, how it looks like, right? It gives you where the maximum deflection occurs. It gives you the slopes at the ends, that is at theta A and theta B. So what are the slopes? It also gives you the equation of the elastic curve. For example, here at x less than A, it tells you that what is the expression for the equation of the elastic curve that you have over here. And in addition to this is for just one of the cases, for many other types of loading, and some of them, if you think about it, we have already solved using our second order method. For example, remember this cantilever where we had gotten the deflection as PLQ by 3I, negative with a negative sign indicating a downward direction. So these are some of the standard things which is there. So if we again go back to the previous example, what we need to do is, from the table I need to find for the UDL case what is the deflection at D, for the simply supported case with a point load what is the deflection at D. I simply need to add up those two deflections to find the total deflection. So for example, here I need to come into this one, simply supported case with a UDL, simply supported case with a point load at my point of interest. Now these are for general dimensions. Now in our beam example, the dimensions are given. You need to simply plug it back and find it out what are the deflections over here, and these relationships are given for many different loading conditions that you have over here. Now the particular problem example, it is not solved here. We are not going to solve that. We are going to solve another example, but you might want to take a look at any one of the textbooks, go to the back pages, pick out the expressions for these standard cases that is there, and then see whether you get for the deflection at D, YD, which I wrote at delta D previously, if you get the deflection and the theta as the same or not. Okay. So now this was the principle of superposition, as you see, as it is applied to statically determinate structures. Now what happens? How can you apply these in statically indeterminate beams? Remember, statically indeterminate beams are those where your simple equations of equilibrium are not sufficient to find the reactions, and consequently not sufficient to find the deflections if you're just starting with the reactions again, right? Now if you take a look at this beam over here, this is one of the examples. This is a statically indeterminate beam with 1 degree of indeterminacy, because we know that here is going to be one reaction here, one moment here, another vertical reaction here. So one you will have from the, even if you use the equations of equilibrium, there will be one unknown reaction that will be there. So degree of determinacy 1. So you need to choose one redundant. So let me go ahead and maybe mark it with a pen, because this is important. You need to choose a redundant. Now there are, in a beam, in a statically indeterminate, there are different ways you can choose a redundant. You can choose different forces or moments as redundants over here. Now as one of the cases, you can choose this RB as a redundant. So now you see, you can boil this down to your one of the standard cases. So if you take a look at this beam, and if you apply the principle of superposition, how do we do this? We can have a cantilever beam with a uniformly distributed load and a cantilever beam with a point load. Simply something like this over here. You have a cantilever beam with a uniformly distributed load and a cantilever beam with the point load. Now we are going to, what will be our principle of superposition, or how are we going to solve this? Now you see here at this point B, in the original beam at this point B, you cannot possibly have any deflection. That is, y at B must be equals to 0. So now since I have taken this one here, for this case I can calculate that what will be the y of B due to the uniformly distributed load from our standard tables. You can do it with the second order method also, but why waste effort? If you take a look at the standard table, you will have a case where we have the uniformly distributed load across a cantilever. I will show you, which is this case, this guy over here, right? In this case, you have a uniformly distributed load across a cantilever, and the other one is a tip load, but only the load is acting vertically up. As you see over here, yeah, you see the load is acting vertically up over here. So what is going to be your compatibility? Compatibility will be this deflection plus this deflection must be equals to 0, because in the original beam, at this particular point, this point is not going anywhere, the deflection is 0. So this is one of the choices of redundants that you have. You can have other choices of redundants also, we'll come and see, but you must keep in mind one thing, that after you designate one of the reactions as redundant, you must ensure that the redundant does not make your structures unstable. So even if I chose the RB over here, I still had the cantilever end, so my structure was still, a stable structure. I did not make the structures unstable by choosing the redundant. Now that we have that, now you determine the beam deflections without the now you find the deflection using this redundant as well, then you add those two together and you use the compatibility over here. So the final deformation must produce deformations compatible with the original support. So see, this is what we have used, is that my sum of these two deformations is compatible with this deformation over here, which is equals to 0 in this particular case, right? So now you can have another choice of redundant. You can choose your moment as a redundant over here. Now once you choose your moment as a redundant, you get something like this. It's the same beam that you see over here, but now I can split this into the case where we have a beam with a uniformly distributed load and another beam where you have this moment which is acting over here. Since I have chosen the MA as a redundant, are these standard cases? Yes, this one we saw as a standard case already. Let's take a look at this one over here. Let me go back to the table quickly. So you will see you have a case where you have a simply supported beam with a moment at the end, also as one of the standard case. You have to keep in mind though that you cannot simply blindly pick these values over here. You have to be worried about whether the moment is acting clockwise, anti-clockwise, whether the moment is acting on the left side of the beam, right side of the beam. Either way, you can use these equations and you can use your logical judgment and thinking that what is the value of deflection or the slope that you are going to take. So once you have that, even with this choice of redundant that we looked at, you can easily solve the problem. So let's go ahead and take a look at two examples. The first example will be the principle of superposition applied to a statically determinate beam. The second one for a statically indeterminate. So this is the first example problem which we are going to solve using the method of superposition. So as you see over here, what we have is a cantilever beam which is partly loaded at the right end L/2 with a uniformly distributed load W, right? And what you see here, this is the standard table which has, for some of the standard cases, the expressions for the deflections and the slope and the equation of the elastic curve that is there. Now if you sort of scroll through this list over here, the only places where you have the cantilever beams are these guys over here. And if you compare with this one and this one, you actually don't have a case where you have just a part UDL. But the question is, can we make use, and the only beam that has a cantilever and a UDL is this one over here. So the question is that, can we use these relationships over here to solve this particular problem? So let's just go ahead and try doing that. So first I'm going to draw these beams as a superposition of two different beams, and then we will use this relationship which is given in this particular row of this standard chart to find the deflection and the slope. So let's first go ahead and draw the beams which when superimposed eventually gives back this beam over here. So what I have drawn, that in the first beam I have spread the UDL from the left end to the right end, similar to this one over here. So now it spans the entire length L, and to get back the original beam I must subtract the L which is at L/2 over here. It is this one. So this total length is L and this one acts over the span L/2. So let me go ahead and maybe mark that one over here, that so L/2, and eventually if you add these two beams you get this particular beam over here. Now to find the deflection and slope at B, so first let's so it asks at B, so at the end tip. So at the end tip, let's see in this one, it gives you the maximum deflection which happens at the end, Y max, as you see over here, that is this expression, and the slope at the end as this expression over. So that is pretty straightforward for the first one. And also let me write this one as beam 1 and this one as beam 2. So for the beam 1, I can directly use the table and write the deflection and slope at B. Now remember, eventually if I can find the deflection and the slope at the end B for this beam over here and add it to the deflection and the slope at the end B for this beam over here, I should get the deflection and the slope at B in the original beam. So let me first write for beam 1 directly from the table. So this is for this subscript 1 here refers to beam 1. So I've directly taken these values from the table and I've put it over here. And how does the beam 1 deflect, and how does it slope downwards? It slopes something like this. And you see for this beam 2, so now the beam 1 is fine. So next we have to find for beam 2. Now for beam 2, the interesting thing is that you see, since it's a part of the cantilever only is loaded, So this beam, if you have to draw the deflection of this beam, it deflects with a slope over here, and after that, since there is no load, it is going to have a straight line. So let's just draw the deflected shape of this beam. It has something like this. So it deflects up to here with a a quadratic curve that is over here, and after that it continues like this over here. So now up to this particular point for this beam, I can find the deflection directly from this formulation over here. Remember, this formulation is valid for a length L. So when you have a cantilever with a length L, now the W starts from one end of the cantilever and continues up to the L over here. Here also it starts at the 0 point and continues up to L over 2, and if you consider the beam as weightless, so essentially suppose this one does not have any weight at all, so up to this particular point we can get the deflection over here using this expression over here. But simply for L, I have to substitute L over 2 over here. Simply here also the slope at this particular point, it is going to be WL cube by 6 EI, but for L I have to substitute L over 2 now, right? But now my question is that I'm trying to find the slope and the deflection at this point over here at B. So maybe let me go ahead and write those different points that are there. So this is A and this is B, and at the central point over here I have point C over here, and here also this is my A, this is my B, and at the center point over C, right? So I'm trying to find everything at this point B. Now you see that if this curves like this and then it continues like a straight line, the slope at C must be equals to the slope at B. So let's just quickly mark that one over here. So here whatever the slope that you will get, and the slope here must be the same. But what about, and if I find the deformation over here using this table, substituting L as L over 2, what about the deformation at this point? It can be easily calculated because I have a linearly increasing function over here with a particular slope. So let's just go ahead and maybe start to write that down. So all I'm interested for this moment is calculating what is my delta at C at in this beam over here, so in the beam 2, and also what is the theta at C for beam 2. So what is the theta? So this, remember this slope, so so this is the word slope, my webcam overlay, so this is the same slope over here. Maybe I erase that and write it below. Right? Yeah, it's clear. So same slope, and this slope over here at this particular point is theta C2, right? So let's just write there. So it's theta C2. So let's just write the expression. So at this particular point C, what is my delta C2 and the theta C2 that I have over here? So this is for beam 2. Also remember, since here the load is acting vertically up, the deflection is up, so this is going to be positive over here. So now I have calculated at this point C over here in this figure. So next I have to calculate at B, because eventually the problem asks to find the deflection at slope at B. For beam 1 I have already calculated at B. For beam 2, from the calculations at C, I simply need to translate them to this one over here. So I know that the theta at C2 will be also equals to your theta at B2. So maybe let's just mark that over here, which is equals to theta at B for the beam 2, but the delta over here I have to calculate that delta based on this deflection delta C2 that I have, and as well as this linear line. So this is linear, so let's just maybe make a note of that. So this is a linear variation that we're having over here. So let's just calculate the delta B for at beam 2. Right, so this is just what I have done over here. This is simply this deflection. This is simply this deflection over here plus the slope times this distance. Remember, this distance is L over 2 because this load is acting over the half of the beam. So if we just go ahead and sort of simplify that, what you will eventually get this expression as equals to, So now what I have is that for both beam 1 as well as for beam 2 at the point B, I have the delta for beam 1 and the theta for B1, and for the beam 2 I have the delta at B2 and the theta at B2 over here. Now I simply need to add them to find the deflection and the slope at B. So if I just go ahead and add them, the final answer comes out as so you see both come out as negative. This one makes sense, it will be negative over here because your beam deflects something like this, that is towards the vertically downward direction of y, and your slope also comes out as negative, so that means you have a clockwise kind of a rotation as something like this over here. Right, so I hope this problem example was clear. So this was the case of the statically determinate example where we made use of the standard expressions in the table, but you have to sort of think that how you want to use the standard, because every problem will be not framed into one of these classic examples. You have to make use of these examples after proper amount of thinking, that which things from the table can you take and apply the principle of superposition to compute the moments, to compute the deflections and the slopes. So this problem example for superposition, it deals with continuous beam where you have two spans, 2l/3. After that you have a roller support and you have another l/3 over here. And what the problem asks you is to find the reactions and the supports, reactions at each of the supports and the slope at the point. This is also an example where your simple equations of equilibrium will not be sufficient to find the support reactions. So you would have to use your the deflection relationships and so on to find the reactions and as well as the slope, right? So we are not going to explicitly solve this particular problem, although we can look at some pointers on how you would approach to solve this problem. Now you see, so since it's a statically indeterminate beam, you have to choose a redundant. Now you can either choose as RA. So here essentially what you have, if you mark the reactions, you have these three reactions which are there, which are RA, RB and RC, right? So you can choose any one of them as the redundants. For example, RA you can choose as a redundant, or RB or RC. Now you see that if we have to be wise in our choice of the redundant to see that which category in these standard tables it follows. Now if you look at the tables over here, it talks about your cantilever beams, and then all the beams which are given are simply supported. So essentially it's probably the easiest to take this beam over here and choose RB as the redundant. If you choose RB as the redundant over here, then you have one beam, that is AC, which has a uniformly distributed load W, right? And you have another beam AC where you have the pin supports and a vertical reaction RB over here. So essentially this beam you can write it as two separate beams. So let's take a look at that. What can we write it as? So your first beam, beam 1, so here I'm choosing RB as the redundant. So this is my beam 1, and beam 2 is going to be again the simply supported beam, but here I will have a vertical reaction RB. So now that you have split your beam into two beams, so you see that over here the summation of the deflections and the slope of these two beams, which eventually give you whatever you want in this beam over here. But now You see here, now you can use the tables. For example, here, because of this load W, remember this particular load is W over here. Because of this load, you can find the deflection which is going to happen at this particular point B over here. Now, what is the compatibility? Now, before looking at the table, what is the compatibility that we are going to use? So we are going to use, see, if in this beam over here at the point B, since you have a roller support, there is going to be no vertical deflection. So the deflection at B, at Y at B, that you calculate from the deflection at B at this particular beam over here, or this particular beam. So here, if you have to go and mark, so this is your point B and this is your point B over here. So here the downward deflection that you will get at this for the beam 1, and here the upward deflection that you will get, if you add them up, must be equals to 0. So that is the compatibility condition that you are going to use, right? So maybe let's make a note of that as well. So maybe somewhere over here. So compatibility is your Y of B, that is your delta at B for the beam 1 plus delta at B for the beam 2 must be equals to 0 over here. And now you can easily use the tables to calculate the deflection at B. You can use this particular row over here, which gives you the equation of the elastic curve. So at here, if you put x equals to 2L over 3, you will easily get this delta B1. And similarly for this one over here, this is the one which is a point load, but now you have to be careful, the point load is acting vertically upward. So for this one, this also gives you, I think, right where you are applying the load, or I don't know, or maybe the equation of the elastic curve, or x equals to a. Yeah, see, x equals to a, that is the right at the point where you're applying the load. It gives you the deflection over here. So you can simply add that up, and you can find the slope at that particular point over here. Now once you will see that this guy over here, once you calculate this delta B2, will come in terms of RB, because it dependent upon the load over here. So that will help you get what is the reaction RB that you have over here once you apply this compatibility. And once you know one of the reactions, the other reactions can be simply computed from your equations of equilibrium. So I will write down the final answers for this particular problem that is there. You can go back and check whether you're getting the right answers or not. So the final answers for this one comes out as so these are the overall answers that you get. That is, the reactions are each of the support and also the slope at the point A. See, the slope of the point A also you can easily compute, because here you are getting the value of the slope at A for this point load case, and also for the UDL case, that also gives you the slope at the ends. So the slope at here as well as here, you can simply add the slopes to find the slope in the final for the final overall structure that you have over here. So I hope with these two problem examples, one for the case of the statically determinate structure and one for this one, the indeterminate structure, you are clear on how to use the method of superposition, and these tables actually come a lot to your help to find these deflected shapes or the deflections, and as well as the slopes. In this lecture, we are going to learn a new method to solve beam deflection problems, and this method will make your life so easy to solve beam deflection problems. You will not want to use any of the other methods, for example the second order method or the fourth order method, or even the method of superposition. So this method, I personally like this method so much, I would maybe rather just go ahead and write it that to solve your beam deflection problems, this is an amazing method which makes your life extremely easy to solve deflections, slopes, and so on, given any type of beam, given any type of loading. So let's go ahead and take a look at this method. So that's the whole objective of today's lecture. And but first, why do we need to learn this? Why can't we just happy with the second order method or the fourth order method or with the method of superpositions? Well, if you think about it, that do you actually need it? Do you actually need to know another method, which is the using the singularity functions over here? So now if you sort of think of the different techniques that we learn, for example the second order, fourth order, or the method of superposition. Suppose, for example, say you have a beam, right? Suppose the beam has say simply supports. and say a multitude or different variety of loadings. For example, let's say the beam has a point load somewhere, say it has a triangular load somewhere, maybe it has a point couple somewhere, maybe it has a uniformly distributed load at the very end over here. Okay. So suppose if you are given a beam like this, where at different points of the beam you're asked to find, say, the deflections or the slope and so on. Even if you do the second order method or the fourth order method, if you do either of these two methods, you see you have to have many different sections to write out your equations for the moments, and then you have to use the support conditions and the continuity conditions and so on. For example, in this problem we are looking at, we have to maybe take a section here, take a section here, here, here as well as here. So how many do we end up with? It is 1, 2, 3, 4, 5 and 6. So 6 different sections. So you will essentially have 6 times 2, so that is 12 constants of integration if you're doing with the second order method, right? And now to solve these constants of integration, you have only two boundary conditions. Remember, the only two boundary conditions are from the beam are y equals to 0 at x equals to 0 and y equals to 0 at x equals to L. So to solve the additional, you will need additional equations to solve all the constants of integration, which you get from the continuity function. That is, at each of these sections you have the, the continuity of the slope as well as the continuity of the deflection. So you see how difficult your life becomes. Now that sort of gives you a glimpse of, if you are using second order or fourth order method, what are the problems. Now you might argue that, okay, you will use the method of superpositions, but see that for this kind of beam, how many different beams you have to break it up. So you have to break it up in a beam with a simply supported with a point load, a beam with a triangular load, a beam with a point moment, a beam with a UDL. You have to find the individual deltas or the individual slopes at whichever is your point of interest. Then you have to go and aggregate and have to add them all back together. So both of these techniques, or all these three techniques, the second order, fourth order, or the method of superposition, it makes your life too tedious. So that gives you the answer that, do we need it? Yes, we need to know a method which will very efficiently solve your beam deflection problem and your beam slope problem. So before going ahead and solving problems on that, first we will have to learn what is the singularity function. And this method was actually discovered by the British mathematician William Henry Macaulay, and it is also known as the Macaulay's method of solving beam deflection problems. So let's go ahead and first take a look at some of the mathematical rules for the singularity functions and how we can apply them to solve the beam deflection problems.